And I
Okay,
would like
perfect.
to move to the next presentation, which of course, the last one, but not the least, coming from a leading cell maker, Jietai. So we have Xinrui An, who is R&D manager at Jietai Solar. He is going to speak on Jietai Solar, bringing reliability and efficiency to PV modules. And Xinrui is going to speak from the perspective of cells. Xinrui, the floor is yours.
Thanks, Rowan. Good afternoon, everyone. I'm Xinrui from JTPV, and it's a great pleasure for me to share how we, as a professional cell manufacturer, can bring reliability and efficiency to PV modules. Okay, so today's talk will cover the following sections. I'll first go through the degradation mechanisms of UVID, DH, and PID one by one, and discuss how they can be combated from a cell manufacturer's point of view. Then I'll show an outdoor test result based on our JTPV Model 1 cell with comparison to another Tier 1 cell manufacturer. Then I'll discuss in correlation with the cell structure and processing. Finally, I'd like to take this opportunity to introduce our latest cut-line technology, which could be quite interesting for some module suppliers. Since 2023, UV-induced degradation has been a very hot topic within the PV community. Although the detailed mechanism of UVID is still not that clear, it is generally believed that the high energy of UV photons can break the silicon-hydrogen bonds at the front surface of solar cell. And this is supported by the fact that such degradation primarily affects the open circuit voltage of a solar cell. And early reports reveal that for a variety of high-efficiency modules, including TOPCon, HJT, and BC, UVID loss can be as high as over 10% relative, and these cells usually have non or lightly diffused surfaces and rely more on the chemical passivation of dielectric layers. But such a high extent of UVID is, however, regarded as a combination of artifacts and real degradation, at least for TOPCon modules by Fraunhofer earlier this year. It is shown that the dark storage after UV exposure can greatly exaggerate VOC and power reduction. A brief light soaking step can easily remove this artifact and is more representative of the real case scenario. But noticeably, even after light soaking, further dark storage can still distort power measurement. Ideally, we need to measure the power immediately after the light soaking. Nonetheless, UV60 in the range of 2 to 3% is quite common for the most of the TOPCon modules under investigation. So UVID is still a problem to be reckoned with, in our opinion. In JTPV, we developed a specific front passivation scheme for customers who require very low UVID. We've made several changes to the front passivation stack. Not only does the surface become less dependent on hydrogen passivation, which is very sensitive to UV, but the amount of total UV absorption by the cell is also greatly reduced. And to make the surface less reliant on hydrogen, we could either increase the thickness of aluminum oxide or make this layer less permeable to hydrogen, which inevitably leads to a lower VOC. And to reduce UV transmission to the cell, we tailored the silicon nitride layers at the front to a higher reflecting index. And in this case, ISC is also slightly reduced. So overall, a slightly reduced VOC and ISC together may cause an efficiency loss about 0.1%. But UV60 is greatly improved from over 2% to about 1%. And note that all the reliability tests we perform are based on common bombs without any UV cutoff or downshifting films. Because as a cell manufacturer, we cannot control the bombs of our clients, so we must test for the worst case scenario. But for module suppliers, it might be very economical to use such UV blocking materials to make trade-offs between module power and long-term stability. Another important reliability metric is the damp heat. It accounts for the module power loss under high temperature and humidity. The main cause for DH is the introduction of acetic acid from encapsulants such as EVA, leading to corroded contacts and increased IS. This process can be accelerated by high temperature and humidity. For the worst case, up to 60% power loss can be found for some early TOPCon modules after DH1000. The EL images show that at least 3 different types of failure patterns exist that include the localized point failure and failure around the contact ribbon areas, and also the failure throughout the entire cell surface. And the point failure is attributed to the chemical reactions between cell contact, moisture, and some local contaminants. While the interconnection failure originates from the chemical reactions between the contact ribbons and possibly the soldering flux that involve acetic acid release. And the last failure for the entire surface is not contact related, but maybe due to some limited types of encapsulant. So in JTPV, on the cell level, we think that the most effective way to mitigate DH degradation is by tuning the composition of the silver paste. We put continuous efforts in reducing the aluminum content and any other components easy to react with acetic acid. We also align our firing conditions recipe to the organic system of the silver paste to avoid any residuals after firing that might be reactive under DH conditions. And finally, also make sure that the anti-reflection coating layer is free of blistering and therefore resistant to acetic acid. But for module suppliers, our advice include using double glass modules, which inherently have less DH problems than single glass ones. And also acetate-free encapsulants such as POE is highly recommended, not only due to its superior DH, but also better PID performance than EVA. And finally, we should never neglect the importance of keeping a clean environment for module soldering and lamination. So the modules made of JTPV mono 1 cells show an excellent DH1000 results of about 3.5% for single glass and 1.5% for double glass modules, both far below the industrial average. Even with DH2000, our double glass modules are still well below the 5% IEC mark. And the third type, the potential induced degradation, is caused by the potential between cells and the module frame, which is usually grounded. And it was first discovered in p-type modules as increased shunting. However, 3 progressive stages are identified for n-type modules, and each of them has a different level of impact on different cell types. The first stage is the polarization type PID, or PIDP. It's caused by accumulation of charges at the passivated interface, and it is usually manifested as a decreased surface passivation that leads to reduced VOC or GSC for the cell. And PIDP can occur with either positive or negative bias. For the n-type TOPCon modules, it mainly affects the front p-type emitter, P+ emitter, when the cells are under negative bias with respect to the module frame. And the kickoff voltage for PIDP can be quite low as 50 watts. So it may impact the small rooftop PV systems and also large PV stations alike. PIDP can be fully recovered by applying the opposite bias, or in the case of the aluminum and silicon nitride passivated p-type surface, simply with the illumination or long-term storage for the charges to dissipate over time. The second stage is the sodium penetration type PID, or the shunting type PID-S. It is equivalent to the shunting problem initially discovered in p-type modules. The sodium ions released from the soda-lime silicate glass or some other contaminants migrate under the negative potential under cells between the cell and the grounded module frame. And over time, they can penetrate the module encapsulant and even the cell anti-reflection coating layer to reach the emitter, therefore creating the shunting path and causing fill factor reduction. And PID-S only affects negatively biased modules, so it can be recovered by simply applying a positive bias or subjecting to high temperature. The most severe stage of PID is the corrosion type PID, or PID-C. Originating from the chemical reactions between sodium precipitates and the dielectric layer, PID-C may lead to total failure of the passivation and even the p-n junction, bringing down the cell voltage and the fill factor. And it also has been found with some MPERT and AGT modules, and it also can be accelerated by the moisture ingress. The major PID type of concern for TOPCon modules is the PIDP. On the cell level, there are a range of measures to counter it. For example, we can use higher refractive index silicon nitride with higher conductivity. or by adding a very thin dielectric layer such as silicon dioxide underneath the nitride to reduce the potential across the silicon nitride layer. And some of these measures are in well alignment with reducing UV. Besides, maintaining a high level of integrity for the front dielectric is also very important. In other words, we have to prevent the ARC from blistering, and we also have to avoid contamination before depositing the front fumes. The aluminum oxide layer has some natural strength in combating PID due to its relatively low resistance for charge dissipation. And for module suppliers, the use of sodium-free glass, high resistance encapsulants, and backsheets less permeable to moisture in the case of single glass modules can be very effective to reduce PIDS and PIDC. And on the system level, the use of the anti-PID inverters and grounding the negative terminal will also be helpful. So with standard bombs, our cells exhibit excellent PID properties for both single and double glass modules, well below the industrial average. Even for the single glass modules under PID 288, the degradation rate is only 3.5%, well below the IC standard of 5%. And earlier this year, we initiated an outdoor testing in China. And the site is in northwestern China with a temperate continental climate and adequate insulation with relatively high UV components. We have two strings of modules for comparison. String 1 consists of 10 modules made with our mono 1 cell, and string 2 consists of 10 modules made from from another tier 1 manufacturer. We call it company A. Both modules are manufactured with the same bombs. So starting from last December, we've been monitoring daily electricity generation and tested the IV characteristics for the same two modules from each string every 3 months to monitor degradation. So all the modules are pre-stabilized and with an initial power around 580 watts. And after 10 months of operation, we can see that our group have slightly higher generation per watt over company A, and the gap is between 0.4% to 1.6%, with a strong seasonal trend. This can be explained by the difference in cell performance. As I just mentioned, JPV, we have a small sacrifice in VOC for better UV reliability. And we also are very prudent in choosing the silver paste. We just avoid the paste with excessively low corrosivity, which can increase cell VOC, but potentially put DH at risk. So as a result, our VOC is lower than company A, leading to a slightly higher temperature coefficient for our module. And the high temperature in summer is more favorable for company A, so reduces the gap between the two groups. And for the selected modules for degradation tests, our products show a much lower degradation of only 0.24%, while company A has nearly 2% after 7 months into operation. And this result highlights our superior UV reliability and shows how it can benefit electricity generation for customers. This slide just shows the daily generation data for certain months in the year, and we can see that the daily gains are quite stable throughout the month. Cell technologies not only impact efficiency and power output, but also affect reliability. For example, our stack wafer depot technique forms uniform and electrically stable backside surface, free of blisters, and it also facilitates reliable rear side passivation. And the front side gradient index anti-reflection coating optimizes the thickness, refractive index, and hydrogen content within each layer to reduce UV and PID losses. And the emitter metal contact optimization uses less corrosive silver paste, free of aluminum, to not only to reduce genome metal, but also enable better DH for the cell. And in addition, the surface stress and the current are more evenly distributed across the cell with our super multi-bus bus structure, leading to better mechanical strength and less heating of the cell. And for our second generation mono 2 cells, the wave back surface field not only increases the cell efficiency by 0.15%, also increases the bifaciality up to 6%. And with highly reflective grounds, they can contribute to about 2% extra power generation. And in terms of reliability, the use of aluminum oxide and silicon nitride stack at the rear means better PID responses. And the other feature of mono 2 cell, the half-cut edge passivation, HEP, not only enhances module power by 5 to 8 watts, but also contributes to more reliable modules. First, our wraparound is limited to the outermost 2 to 3 fingers, thus having no impact on welding or module aesthetics. And more importantly, moving the laser cutting step to the cell end effectively warrants 100% laser cutting yield for module suppliers. And in addition, rebinding the half cells after HEP makes their characteristics more concentrated, and this can alleviate mismatch losses that can lead to hotspots. So generally speaking, N-type modules have the strength of being LED-free, good PID resistance, lower encapsulation loss, lower temperature coefficient, better weak light performance, and consequently higher power output and reliability and more reliability. And this slide just summarizes the module power output from mono 1 and mono 2 cells. Both cell types come in a variety of common wafer size and module formats. For the most popular 66210R module, mono 1 can reach up to 630 watts, while a further increase of 15 watts can be achieved with mono 2 cells. And in this part, I would like to share some information about our latest cut line technology, which serves as an alternative but more versatile technique than HEP. As we know, during laser cutting, the damage of and edge recombination are the most severe in the emitter region rather than in the bulk of the wafer. So they can be greatly reduced by removing the emitter along the cut lines. During cell fabrication, the emitter can be locally etched away right after its formation, and the exposed surface will be clean and well passivated by aluminum oxide and silicon nitride, just like the rest of the front surface. Higher reflectance at those spots only causes very negligible effect on cell efficiency due to the very tiny area fraction. For our standard process, the lines are only 300 micron wide, and for one cell, there will be only like 2 or 3 lines. But they can be made wider if the clients need larger tolerance for laser cutting. And this slide summarizes some of our initial results about CLT on different module formats, including the half cut, the third cut, and the quarter cut. The baseline in each group means that all the laser cut edges are not treated, whereas the CLT means that the edges are treated with CLT treatment but not passivated by aluminum oxide like in HEP. Since all the groups are based on different module formats and involve different module techniques, so you cannot compare the power across the groups. But within each group, it is very obvious that CLT may increase the fill factor, and that's the module power. And also, the more pieces cells are cut into, the larger the power gain is. For the half-cut cells, 3.2 watt power increase is achievable, while for a quarter-cut module, the gain is dramatically increased to near 8 watts. And the best part of the CLT is that, unlike HEP, it is easily deployable to different cell formats. You can change the laser pattern very swiftly. And it also offers edge passivation for module suppliers who can only process 4 cells. And finally, for those who are not very familiar with GTPV, here's a brief introduction. We are a wholly owned subsidiary of Jietai, a Chinese A-share and H-share listed company. We dedicated ourselves to N-type solar cell design, R&D, manufacturing, and sales. With an annual capacity of 44 gigawatt, we have a shipment of 45 gigawatt during 2024 and H1 2025, and with a cumulative N-type cell shipment totaling 67 gigawatt. And apart from the product performance and the reliability, we also highly value overseas markets, and we put a lot of effort into ESG building, as we obtained the ADME certificate and the shades of green from S&P. This is the end of my presentation. Thanks for your attention.
Thank you, Xinrui. I think that's a very nice summary about the reliability aspects of from the cell side.